Our next speaker is Zoe Liebowitz here from the Imperial College of London. She works on the Devito project. Really cool project. I was lucky to get to know some of the people when I came to Georgia Tech. Matthias was there at the time. And they do really cool things with stencil-based operations that parallel lots of cool things that have happened in finite elements. And she's going to tell us about what she's been doing for matrix routines. Thanks for joining us, and please take it away.
Hi, everyone. So today I'm going to be talking about my PhD research, which is on automatically generating matrix-free routines for PDE solvers, but from a very high-level symbolic specification. So the main idea of this talk is about writing PDE software that is reusable and also portable and also capable of solving a broad range of different problems rather than being really tightly coupled to one specific problem of interest. Oh, it's not going. So I'll start the talk with a bit of a refresher from my talk last year at the previous PETSc meeting, so especially for those of you that weren't there. So I'll talk a bit about why people care about domain-specific languages. What is the software Devito? What are some of the things that Devito is currently lacking? What are my new contributions to the software? This involves all of the PETSc integration. And what are my updates since last year? And then I'll present some new results and talk about potential next steps. So what is the main motivation for this work? Well, traditional approaches to solving PDEs present many challenges because they often lead to these very large, complex code bases which are difficult to maintain and difficult to adapt to modern computing environments. Even though I don't personally have much experience developing on such large legacy codes, I've heard plenty of horror stories from people who have about them. So I've been told that they're often tied to a specific discretization scheme and also sometimes tied to a certain dimensionality as well. And so when it comes to exploring different numerical schemes, it becomes a huge nightmare because coding them up takes enormous amounts of time and effort. And when it comes to portability, well, these traditional frameworks often struggle to port their codes onto new hardware, like GPUs, for example, because, again, it often involves a lot of rewriting, which is very time-consuming. So how do we write PDE software that is reusable, maintainable, and portable without spending months rewriting or retuning the code every time the numerical scheme changes or the hardware changes? So this is where DSLs come into play. So they really help us decouple the maths itself from all of the complexities that come with HPC. Instead of getting really bogged down in the low-level implementation work, scientists and engineers, well, they can express their models in a very high level and let the DSL take care of generating all of the efficient code behind the scenes. Even though it can take some time to develop new features into domain-specific languages, once the right abstractions are there, the gains in productivity can be huge because it means that people can try out new ideas faster, and it also actually makes it a lot easier for scientists and engineers, it makes it easier for scientists to work with HPC experts because things are just faster. So that leads me to the DSL and compiler Devito. So Devito is used to generate explicit finite-difference operators. The users can also express other less standard types of operators like sparse operators for interpolation, for example, which are very important in practical applications of finite-difference solvers. So the DSL is embedded into Python. We have this very friendly, easy-to-learn symbolic API. And Devito will automatically generate the optimized parallel C code for you. And the generated code can be targeted to many different architectures. So one key thing to note is that Devito generates very fast code that meets and often surpasses production-grade code. I was told for a while that there were claims like, it's a DSL, it will never outperform our in-house codes. But then as Devito's performance continued to improve, people slowly stopped saying that. So yeah, there are many users in both industry and academia. The main application areas at the moment are in geophysical and medical imaging frameworks. And Devito operates as an open core model, so we have open source Devito, and then there's also Devito Pro, which offers the additional features like the CUDA HIP and SQL code generation backend. So what is the actual vision? Well, the idea is that users write their PDE in symbolic form, pretty much as it looks on paper, and then Devito will automatically generate the low-level C kernel for you. So this means that users can really build very optimized solvers in just a few lines of symbolic Python. One example, which I'm sure many of you know of, is Phi-Drake, and this has been proven very successful for the finite element method. And Devito is similar. It raises the level of abstraction, but for finite differences, and it does it by building on top of SymPy. So just to give you a sense of what the API looks like, I'll just show you how to build a very simple 2D diffusion operator in Devito. So first we import the required objects to specify our finite difference scheme. So for that we need a grid to specify our computational domain, any Devito function objects which are used to encapsulate the fields that we're solving for. We have the equation object, which is used to symbolically express our PDE, and then the solve object is used to specify a time-stepping scheme, and then the operator, which is where all the magic happens. This is what generates the low-level C kernel through a sequence of compilation passes. So we create our computational domain by passing in the shape and the extent. So this is a 2D problem, so we have two numbers for the shape, and the extent is the physical extent of the grid. The shape is the number of nodes in each dimension. Then we define our functions present in the PDE. So here we're using a time function object in Devito. These carry the multidimensional data, and they sort of behave like MPI-aware NumPy arrays. We then define the PDE using the equation object and use the solve object to rearrange the equation to represent our time-stepping scheme. So here solve is used to rearrange equation to represent the field f at the next time step. So f.forward corresponds to f at the next time step. And then you can similarly express your boundary conditions in symbolic form. And then once you have your update expression and any boundary conditions, you then pass these to the Devito operator, and this will generate the low-level C kernel through a sequence of compilation passes. Then we JIT compile and execute our operator by passing in any of the required arguments, such as the number of time steps and the time step size. So here's just a snippet of the automatically generated code for this problem. So there are many adjustments that users can make in the DSL that will generate different low-level code. So many aspects of the user's model are very tweakable, and one key example is the flexibility in terms of the numerical scheme. So users can adjust the space order parameter of these function objects, and this will generate very different low-level code. So here we have second order and a 12th order discretization. So I briefly mentioned before that the main application areas at the moment are in geophysical and medical imaging frameworks. But throughout the development of Devito, there have been many people asking about CFD examples, and what sparked my research is what do we need to do in Devito to be able to tackle these types of problems. Even though, well, there are state-of-the-art sort of finite difference code bases out there for these types of problems. For example, in wind farm simulations, we have Wink3D, but again, these are very large Fortran code bases, which perhaps lack the flexibility that these DSLs could provide us with. But in order to even start tackling problems of this type in Devito, we need iterative solver functionality. And so this has been my work. I've been working on automatically generating matrix-free routines in Devito to interact with PETSc solvers. So in the last PETSc meeting, the sort of flexibility of the Devito compiler for PETSc integration wasn't really there. So a big focus since the last meeting has been on automation. So I spent quite a lot of time building the compiler infrastructure in Devito to be able to generate general sort of PETSc C code. So here we have a flow chart sort of outlining the compilation pipeline in Devito, where we go from the symbolic PDs to the actual executable code. So a lot of the groundwork for PETSc integration actually happens before we even reach the Devito compiler in this PETSc lowering stage. And this is why the new API object PETSc solve. So in this pass, we sort of attach lots of metadata to the symbolic PDEs so that it will trigger the lowering to PETSc later down the line in the operator. So once users have used the PETSc solve API object, they would then pass this to the Devito operator, which will sort of work through the sequence of compilation passes shown in blue here. So a lot of the PETSc integration at the compiler level happens at this iteration expression tree lowering stage. So this is where we actually build all of the callback functions and all of the routines that are required by our matrix-free solvers in PETSc. We set up various solver components, including the DMDA, for example. We also generate all of the structs that are required by all of these routines to actually access information. We also set up all of the PETSc calls that are required to actually set up and run the solver itself. So hopefully to make this all a bit clearer, I'll just work through an example of something that you could now solve in Devito using the new PETSc integration. So some of the new capabilities include solving mixed problems in Devito. So thanks to Ed Buehler, I've taken this example from his very useful book, where we're solving the biharmonic equation as a coupled system. So with this substitution, we get this triangular block form, and we manufacture a polynomial solution to check that our solver gives us the convergence that we expect. So this is how you could now formulate this problem in Devito. You build the computational domain using the grid object. We define any of the functions that are present in our PDs. So we're solving for both U, V, and then we had the F, which is on our right-hand side. So we set up our right-hand side, and then we symbolically express the PDs using the equation object. And then once users have set up their PDs, they pass this to the PETSc solve object, which is the new API object, and this will trigger the lowering to PETSc later on. So they specify the targets and a list of equations. Note that the API is still evolving, particularly for mixed problems. Eventually, we hope that it will probably look more like the SIMP interface for solving mixed problems. But for now, you use a dictionary when you're solving for two fields and, pass in the equations. And then users can also specify their solver parameters. If you're familiar with Phydrate, we've taken a lot of inspiration from them for this. So we specify the KSP type as GMRes because it was a non-symmetric system. And then users just pass the solver to the operator, and this will generate the low-level C kernel. Then we JIT compile and execute the code. So here are just some snippets of the automatically generated code for this particular problem. As you can see, it's not all shown here, but we're generating hundreds of lines of PETSc C code from just 10 to 20 lines of symbolic Python. So in the top left, we have various calls to set up and run the solver. As you can see, we've set up the 2D DMDA because it was a 2D problem. It set the number of degrees of freedom at each node to 2 because we're solving both U and V. In the top right, we have the residual callback, and then in the bottom, we have various routines that are used to set up the matrix-free solver. So does this generated code actually work? Well, here I've got a convergence plot of the two fields illustrating the second-order convergence that we would expect. So the API is designed to be very flexible. PETSc solve it will accept various solver parameters. It's still fairly limited. We hope to extend this in the future, but you can change the KSP type, for example, set your preconditioner type. You can change this, but there's lots of work to be done on this. If you're solving for a single field, this is the current API where you have, you have a list of equations, and you specify your target. The reason that it's a list is because users can set up equations that specify their boundary conditions and pass these to PETSc solve. This will have various metadata attached to them that the Devito compiler will understand. That the Devito compiler will apply the boundary conditions to the correct nodes, for example. And then if you want to solve for more than one field in a mixed problem, you use the dictionary, which I showed you in the previous example. If you want to build more than one solver and pass these to the Devito operator, that also works now. If you wanted to run multiple different SNES solvers, for example, within a single time step, that's also possible. So I'm currently in the process of stress testing the compiler and checking for correctness on various 2D and 3D problems. There's lots to do. We'd like to build a more powerful abstraction. So, of course, we'd like to implement abstractions for geometric multigrid in Devito and get Devito to generate the interpolation and restriction matrices, or operations matrix, and pass them to PETSc matrix free. But yeah, there's a lot of work to do in Devito to do this because we don't currently have a concept of like a grid hierarchy in Devito. So this is all things that I need to do. There are various other improvements to be made. One of them I'd like to figure out, I'm planning to speak to Matt about this at some point after the meeting, but figure out how to remove the essential boundary conditions from the global solver, but I'm using DMDA, so it became a little bit complicated, yeah. Of course, in finite difference frameworks, it's common to use staggered grids, so this is another thing that we need to think about of how to interact with PETSc and how to do this. Devito already supports staggered grids, but getting this to sort of work nicely with PETSc is something that I need to think about. I'm not sure if we're going to use dmstag. I don't know yet, but potentially. So yeah, just to summarize, I've built these new compiler passes in Devito to be able to enable iterative solver functionality in PETSc. Our goal, of course, is to produce this very flexible, maintainable framework that can be used to solve a broad range of different problems rather than just solving one specific problem of interest. We can now tackle more problem cases, such as incompressible flow problems in CFD. That is our goal. But yeah, with all that all said, we're very much in the development phase, and if anyone has any suggestions or comments, then we're very open to hearing them. Yeah, thank you. Any questions?
David? I think you said that Devito can only handle one level at a time. It doesn't have concepts of multi-level. So is there like coarsening and refinement operators?
No, so that's something that I'm going to be working on this year, like introducing the concept of like a grid hierarchy. We need some kind of grid hierarchy in Devito. And then, yeah, the idea is that we will generate the matrix-free operators in Devito for those interpolation and restriction operations and then pass them to PETSc. But, yeah.
Yeah, follow-up question to that. Can it handle curved grids?
I don't think we do. Jack, do you know if we support?
Yeah, so the stuff Ed was doing, the immersed boundary.
Oh, yeah, immersed boundary.
Non-straight boundaries. One of the options was curved grids. The other was this immersed thing, and that's the immersed solution was what was chosen. We could probably talk about this afterwards and go into details and show you some examples.
Yeah.
So yeah, the cost of implementing the curved grid compared to the immersed grid was a design choice at that stage.
Yeah. So there is the immersed boundary functionality, which a PhD student spent his time on, but it's not actually merged into Devito yet, but I think he's working on actually getting that into main Devito. Yeah.
I'm curious as to how you, or if you serialize the representation like to Unicode or YAML, or if anybody's put any thought into that and whether you could do a round trip.
Sorry, could you say that again?
So you have your symbolic representation of the equations in your DSL embedded in Python.
Yeah.
And so those are PDEs that should be representable, like in LaTeX or just in Unicode.
Oh, I
that already has
see.
those representations. And the reason I'm asking is because I work with a lot of these legacy codes.
Yeah.
I used to my own, but even old, like most of the codes used in geosciences are 20 years old. They have their equations hardwired in, but I've kind of had this hope that at some point there's always these pushes to embed metadata.
Yeah.
Right? So I'd really like it if people started embedding the equations that they claim to be solving in
Yeah.
the metadata for their data sets. And so
Yeah.
if you could serialize your definitions that way, and then you could do a round trip and read them back in, then we could convince other people to put the metadata for their equations
Yeah.
in there, and then we could generate validation codes,
Yeah, that's really interesting.
methods. But I didn't know if everything is just Python for now.
Underworld does that. So SymPy has a 2 LaTeX, and Underworld uses the similar SymPy representation to Devito, and you can print out all the equations. I don't think you can read the LaTeX back in, but you can serial pick them and then read them back in.
That's right, yeah.
Yeah, you can do that in Devito as well. It's just SymPy. So you can pick up the SymPy object and read it back in later, and it's got the LaTeX representation.
Yeah.
Representation.
Yeah.
Oh, no, go ahead.
So this tool, can you basically build the entire solver
Sorry?
from the beginning to the end?
Build the entire solver.
Yeah.
Yeah.
Now, can I use that piece by piece? For instance, what if I just need to use this symbolic operation just to build this internal force, for instance, or maybe just Jacobian, and I want to use other solver to build this.
Sorry, I didn't quite hear that.
So you want,
Just a piece of it. Yeah.
so like if you had the full equations, but you just want to pull out the Jacobian application
Yeah.
or something like that?
Yeah.
I don't know. I mean, have you thought about is the end result of this going to always be a monolithic solve operation that you can call, or is the idea to expose just interpolation as a Devito type of thing, like something that exists in the Devito ecosystem?
Yeah, that's interesting. I don't think we've really thought that far ahead. I guess we could abstract those things in Devito. Yeah, maybe at some point. But
All right. Let's thank our speaker again.
okay.